Hello and Assalamualaikum. This is an example of numerical differentiation for first derivative. Here is the question. Use forward, backward and centered divided difference to estimate the first derivatives of this function at x equal to 0.5. So if we say that the first derivative is the df dx, what is the value of df dx at x equal to 0.5? And we are going to apply first forward divided difference, and then after we got the solution we apply for backward divided difference, and lastly for using the centered divided difference. So we are going to compare the approximation using these three different methods, and for each method we are going to use two different step size, h equal to 0.5 and the other one is a smaller step size, which is half over the first step size, 0.25. So the question asks also to calculate the true percentage relative error for each approximation. So meaning you are going to have about 6 approximation. The first one is the approximation from forward divided difference with step size 0.5, and then the second approximation is the solution from forward divided difference using a smaller step size 0.25. So we have another pair of answers for backward divided difference using two different step sizes, and the other two from the centered divided difference with two different step sizes. As the question instructed to calculate the percentage true error, so we need to find first the analytical solution. Since we have that function is a polynomial function, it is quite easy to differentiate it analytically. So we only do that if we are asked to solve it analytically and find the true error. But if you are not asked to find the true error, you can also do that. You can also calculate the analytical results for the comparison purposes, of course. So the first derivatives of the given function is f prime x equal to 1.5 x squared minus 0.2 x plus 0.8. It's quite easy to be determined. Since we are looking for the value of the first derivative at x equal to 0.5, we simply substitute 0.5 into this f prime x, in which we will get 1.075. Let's recall the formula for the forward, backward and centered finite divided difference. We start with the forward finite divided difference, backward and then centered finite divided difference. After we have seen the formula of the forward, backward and centered divided difference, we understand that we need to find these three values: the function at xi minus 1, at xi and at xi plus 1. The question asks you to calculate the first derivative at x equal to 0.5. So 0.5 is our point of interest, and we can say that the xi is at the location of x equal to 0.5. Xi is equal to 0.5. So we can start calculate the value of the function at 0.5, and we have this negative 0.2625. For question A, where the question asks you to solve using a step size of h equal to 0.5, it means that xi minus 1 is 0.5 minus 0.5, so xi minus 1 is equal to 0, and xi plus 1 is 0.5 plus h equal to 0.5 plus 0.5 equal to 1. So we are looking the value of function at x equals to 0, and we are going to calculate as well the value of the function at x equal to 1. So the value of the function at x equal to 0 is minus 0.7. And the value of the function at x equal to 1 or f1 is equal to 0.5. So we need these three values, okay, the negative 0.2625, negative 0.7, and 0.5 in order to calculate the value of the first derivative using these three methods. So let's start using the forward finite divided difference. There is again the formula. So for forward finite divided difference, we only need two values, the values of the function at xi plus 1 or the value of the function at 1. And we also need the value of the function at xi or the value of the function at 0.5. So we simply substitute the values into the formula. So we have the first derivative at x equal to 0.5 equal to 1.525. This is the approximation of the first derivative at x equal to 0.5 using forward finite divided difference. As we have calculated already the true value in the previous page, we can calculate the true error as well as the percentage true error by using the formula that we have learned and used so many times. After we have calculated or approximated the first derivative at x equal to 0.5 using the forward finite difference, now we can calculate the same problem. We can solve the same problem but using different method, which is backward finite divided difference. Revisiting the formula of the backward finite divided difference, the one in the purple box, we can see that we need the value of the function at xi minus 1. We have determined just now if we have step size equal to 0.5, it means that xi minus 1 is equal to 0. We substitute all the values previously evaluated, and we will get the value of the first derivative at x equal to 0.5 equal to 0.875 using the backward finite divided difference. Take note that the value is, the approximation is different compared to the approximation obtained from the forward finite divided difference. When we calculate the true error, we can see that the true error is a lot smaller than the error obtained from the forward finite divided difference. This can be something, but in general, it can be safe saying that actually the error is quite the same when we compare the forward and the backward finite divided difference, because it might depends on the problem, the specific problem. Now we can move to the centered finite divided difference, CDD. Okay, that's the formula. So we need the values in the function for x equal to I plus 1 and the function at x I minus 1. Simply substitute those values and we get the first derivative at 0.5 is equal to 1.2 when we approximate using the centered finite divided difference. The true error is also small and even smaller compared to the backward finite divided difference. So we can summarize all the approximations after we solve using three different methods but using the same step size. So the step size was 0.5. We have these three methods: forward, backward, and centered divided difference. So here are the approximation for the first derivative at x equal to 0.5 and their respective true error. So we can see that the largest error was from the forward finite divided difference. The rest has small error. This is the second part of the problem, where actually we are still solving the same problem This time we use smaller step size, which is 0.25. It is half of the previous step size. It means that we need to re-evaluate the value of the function at xi minus 1 and the value of the function at xi plus 1. The value of the function at xi is still the same because the interested point or the value that we are solving is at x equal to 0.5. So we are looking the first derivative at x equal to 0.5. But when we change the step size, it means that we also change the value of the function or the value of the xi minus 1 itself and the value of the xi plus 1. So using the step size, we can determine the value of xi minus 1. This time xi minus 1 is 0.25. So we can calculate the function at 0.25 and we have here 0.4984. And then we calculate the new value of xi plus 1, simply 0.5 plus the step size. So we have 0.75. And then we can calculate the value of the function at the new value of xi plus 1, which is equal to 0.0547. So we can repeat the same procedure that we have done in the previous calculation. We can calculate the forward divided difference, backward divided difference, centered divided difference, similar as what we have done using this method for the bigger step size. So in summary, I simply put all the answers into the table. You can try it yourself to do all the working calculations by yourself and make sure you get the same answer. It means that you get the correct calculation. So the approximation of the first derivative at x equal to 0.5 using the forward divided difference is 1.2688 with the true error is 18.03%. So if you compare with the previous calculation using bigger step size, the true error of the forward divided difference is almost similar to the true error for the backward divided difference when it used the larger step size. So as expected, the results of the backward divided difference is having a smaller true error, 12.2. And you can see that CDD, the centered divided difference, produce a very small true error, which is 2.9%. So as expected, using smaller step size, in this case H, will produce better approximation. Now we put it side by side, the approximation of each method from the H equal to 0.5 and the approximation of all method using a smaller step size or half of the original step size. We can see for FDD, the first row, for FDD it improved quite a lot from 42% to 18%. For BDD it also improved when you reduce the step size, but not as much as the FDD. And you can see the centered divided difference. Before you reduce the step size, the error is already small. In fact, the error is a lot smaller than the FDD and BDD. And the error of the CDD using H equal to 0.5 is still smaller than the approximation of the FDD and BDD using H equal to 0.25. When you reduce the step size for CDD, the centered divided difference, the true error also reduced significantly from 11.63% to 2.9%. This condition can be reflected based on the estimate of error for each method. FDD and BDD have estimate of error OH, meaning that the estimate of error is proportional linearly to the step size. But CDD, the estimate of error of CDD is OH square, where the estimate of error is quadratically proportional to the step size. That's why you can see by improving the step size, you can see the CDD improves significantly. And even before you reduce the step size, you can see that the CDD is having a much better approximation compared to the other two methods.